Welcome everybody to today's webinar. This is Maria Blaise Costello and I'd like to welcome you all to today's event. Today's webinar is being hosted by the Clean Energy States Alliance as well as the Northeast Electrochemical Energy Storage Cluster. Our topic today is distributed wind technology for hydrogen production, and today's webinar is going to be hosted by Val Story, our project director. So welcome everyone. Before we begin, I'd like to go over a quick housekeeping slide with you. All of you today will be in listen-only mode, so we will not be able to hear you. Given that, if you have computer speakers that you can turn on, feel free to access the audio portion that way, or if you'd like to use your phone, that's totally fine, but we ask that you please enter your PIN number onto the telephone keypad. As you see on the screen here, there's a question box. We're going to ask today that all of you submit any questions that you may have for our presenters at any point during today's broadcast by typing them in and hitting send, and we will queue up your questions and we'll ask them as time allows following all of today's presentations. So please enter questions here in the question box, hit send, we'll queue them up, and today's Q&A is actually going to be facilitated by Todd Olinsky-Paul, who is the STAP project director for energy storage. Val has to leave and Todd will take over the Q&A at the end. This webinar is being recorded and it's going to be posted on the Clean Energy States Alliance website, which you can see at the URL here. So by the end of the day, you should be able to find the webinar recording as well as the PDFs of the presentations. So with that, what I'd like to do is introduce Val Story. She's a project director here at the Clean Energy States Alliance. So Val, please go ahead.
Hi, thank you, Maria, and thanks to all of you for joining us, and many thanks to our three panelists for taking the time to pull together presentations and for being here today. This webinar is being hosted by the Clean Energy States Alliance. We're a national nonprofit, and we work with states and other organizations to promote clean energy policies, programs, and technologies. Next. To that end, one of the groups that we work with is the Connecticut Center for Advanced Technologies, which is a co-host for this webinar. Together, we run the Northeast Electrochemical Energy Storage Cluster, otherwise known as NEESC. It's been running for 4 years now. It's a network of industry, academic, government, and non-governmental leaders working together throughout the Northeast to help businesses provide energy storage solutions. It's funded through the US SBA, the Small Business Administration's Innovative Economies Initiative, and it's, as I said, it's administered by CCAT. Next. A little bit about today's guest speakers, and then I will introduce the goals of today's webinar. We have three panelists. We have Steve Szymanski from Proton OnSite. Steve is the Director of Government Business at Proton OnSite. In this role, he's responsible for developing strategic relationships and advancing business and research opportunities with government agencies and government primes in the areas of regenerative fuel cells, renewable hydrogen generation, and hydrogen fueling systems. He has a Bachelor of Science in Chemical Engineering from Cornell University and a Master of Science in Operations Management from Rensselaer Polytech Institute. After Steve, Tara Schneider-Moran will be presenting. Tara works at the Town of Hempstead in New York in their Conservation and Waterways Department. She graduated from Cornell University in 2002 with a BS in Natural Resources. And in that same year, she began working for the town as a conservation biologist, working with various stakeholders to study and protect avian breeding populations. Under the leadership and guidance of Commissioner Ron Masters and a strong interest in energy technologies, Tara began writing successful grants, resulting in over $8 million in private, state, and federal funding towards renewable energy projects for the town. And then the last presenter is Kevin Harrison from the National Renewable Energy Laboratory. Kevin is from Rochester, New York, where he completed most of his education. He began at NREL as an intern in 2003 and was hired in 2006, and since then he's been the lead in all aspects of NREL's Renewable Electrolysis project, including the Xcel Energy NREL Wind 2 hydrogen project, which we will hear about today. So to that end, today's presentation is on distributed wind for hydrogen applications, and we chose this topic because CESA runs a distributed wind project called ITAC, the Interstate Turbine Advisory Council, and we're always looking for ways to promote the distributed wind market. So we thought this is a potential emerging market of interest to distributed wind stakeholders. Likewise, through our partner, the Clean Energy Group, our sister organization, we run the Resiliency project, which is managed by my colleague Todd Alinsky-Paul, and that project works with states and local officials to support greater investment in power resiliency. And of course, I mentioned our work with NEESC. So today we're going to learn about electrolysis, the technology status, and its commercial prospects of electrolyzing hydrogen through wind. We're going to learn about the best applications for this technology and the broad applications for hydrogen. We'll learn about the current market pull, both geographically and in what applications this technology makes sense. So to that end, Proton will explain electrolysis and their commercial products, the emerging markets for hydrogen, which includes energy storage systems. And then Tara Schneider-Moran from the Town of Hempstead will talk about their wind-to-hydrogen installation and give us a bit of a case study. She'll discuss how and why the town chose this technology, how the systems have been performing, how it's been accepted by the community, and how the town funded this project. She'll also talk a little bit about their future plans. One reason I mentioned resiliency is that in the Northeast, resiliency is a hot topic right now given the recent round of storms that have knocked out power in many of our towns. So what are the applications for this technology for power resiliency? And lastly, Kevin will tell us about NREL's work in testing renewable electrolysis, which the NREL began in 2005 with Xcel Energy and Proton OnSite, and he'll talk about the goals for reducing costs and improving overall system efficiency and getting this technology to scale. So with that, our first presenter, Steve Szymanski.
Okay, thank you, Val, and I'd like to thank the Clean Energy States Alliance and NEESC for sponsoring this webinar. And what I will do today is talk about our perspective as a commercial electrolyzer company, how we see selling our products into applications where we're using electrons from wind and potentially other renewable sources to make hydrogen as an energy carrier or a commodity chemical, because I think that's also a reasonable market. Let's see if I can advance the slides. There we go. So just a quick overview of who we are. Proton OnSite is a manufacturer of different on-site gas generation products, but fundamentally our core technology is PEM electrolysis. And that's really kind of our core business. We have over 2,000 systems fielded in 75 countries around the world. So we are a global manufacturer of equipment, but all of our operations are here in Wallingford, Connecticut, as you can see from the picture below. I'll just kind of touch on kind of our product platforms, and we've got several lines of commercial hydrogen generators that we sell into applications that in many cases have nothing to do with energy storage. A lot of our customers buy these hydrogen generators for the chemical properties of hydrogen that they need for their processes. And so, a lot of the products that we sell are for, industrial applications for hydrogen, where you might be using the hydrogen as a cooling media for turbine generators, or you might be using it as for its reducing properties in different manufacturing processes such as heat treating or printed circuit board manufacturing. But what I'm going to focus on primarily is the emerging markets on the right, which are all focused on using hydrogen for energy storage or as an energy carrier. And broadly, the three kind of markets that we see a lot of opportunity for in terms of using hydrogen for those purposes is fueling for vehicles, biogas, process enhancement, and then broadly renewable energy storage. And really, I think a lot of that focuses on wind, which is the subject of our discussion today. One of the things I like to point out when I talk about our company is that we're a profitable company, which in the hydrogen space is pretty significant because there's not a lot of companies that are involved in this kind of activity that are making money, but we have been growing steadily and we have achieved profitability. And the things fueling that growth are there's a very good market for our products in analytical laboratories, and we see a lot of growth here in the U.S. and overseas. Power plant markets, I mentioned that hydrogen is used for cooling turbine generators and power plants, and we see a lot of growth potential in the Middle East and Africa and in Asia. More and more we're doing large projects where we're integrating our equipment with other devices to create a complete system, and we are getting involved more and more in containerizing that equipment. So that is something that is a growing area for us. And we have a larger product platform we released a couple years ago that's helping us to address larger hydrogen requirements such as fueling and semiconductor applications. But ultimately, we see a lot of the growth potential enabled through even larger scale electrolysis, megawatt scale electrolysis systems. And I'm going to talk quite a bit about that in the rest of the presentation. Just a quick kind of overview of PEM electrolysis. PEM electrolysis, I like to point out, is a fairly old technology that's been around for a while. And I also like to point out that Proton has a direct legacy to the innovators of PEM technology at General Electric Research. Our company was founded by a group of engineers who came from United Technologies, and United Technologies bought that PEM Electrochemical technology business from GE Research in the late 80s, and that's when I joined UTC. And so I like to say that I've been kind of working in this area for over 25 years now. And but PEM electrolysis and PEM fuel cells are closely related, and so we benefit quite a bit from advances in PEM fuel cell technology, which have been largely focused on the automotive market, and a lot of the electrochemical and material advances in PEM fuel cells are transferable to PEM electrolysis. And just to underscore the idea that this is really a robust and hardened technology, we sell cell stacks that end up in submarines in the U.S., the U.K., and the French submarine fleets for oxygen production, because one of the side products of electrolysis is oxygen, and for quite a few years now, all of the nuclear-powered submarines in those three navies have been produced. The oxygen has been produced by electrolysis, and so we're very proud to say that we have cell stack technology that's hardened enough to support this kind of critical life support application. So now I'm going to talk about why hydrogen has so much potential value in broadly in the energy ecosystem. And one of the things that I like to point out in this diagram kind of does that is that once you've taken a source of electricity, whether it's renewable electricity or it's grid power, and you make the hydrogen, you have a valuable commodity that can be used for a number of different vectors, a number of different revenue streams. And so this picture just kind of gets across the idea that, you can take the hydrogen and convert it back to electricity via fuel cell for, some kind of a, energy arbitrage kind of application. You can put the hydrogen in cars. Certainly there's been a lot of attention paid to using hydrogen for transportation fuel. I touched on biogas conversion. There's a lot of biogas plants in Europe where putting the hydrogen into the process helps to enhance the conversion efficiency. And then there's been a lot of talk about, natural gas, pipeline injection, the so-called power-to-gas application. And that's another, form of storing hydrogen where you're kind of, bridging the electricity utility silo with the, natural gas utility silo. Just a couple of quick charts to show where we think hydrogen plays in the energy storage market. And, this is, I've seen lots of different, kind of segmentation charts for energy storage. And this one I like because it's fairly understandable. Basically, you can see the segments are kind of split up in time spans. And really what it's saying is that, hydrogen really plays at higher power levels and longer time spans. So you can see that, it's showing the hydrogen regime kind of in the day to month kind of range as opposed to, minutes to hours or something like that. So, that's the key message from this is compared to other energy storage technologies, we really think that it plays in higher power, megawatt scale and higher, and then in the area of, days to, say, weeks, that kind of time span. The next chart, kind of shows how, from a cost perspective, how hydrogen and, a hydrogen fuel cell application kind of scores against other energy storage technologies. And, it's, I'm not sure how easy it is to see, but, basically the hydrogen fuel cell low target is the orange curve that is kind of along the bottom. And then there's kind of a high or kind of a mid-range target that's a little bit higher than that. But ultimately what you see is that the hydrogen curve is, very close to compressed air storage, and also, maybe even a little bit better than pumped hydro. So in terms of cost, and again, this is kind of a normalized cost per kilowatt year, and it shows that really hydrogen energy storage really is cost effective at longer time durations. And I just wanted to give just a couple examples of, kind of real-world, projects that we've done that exemplify the idea that, once you make the hydrogen, there's different value streams that you can get out of it. And this was just a project that we did a number of years ago with Synthetic Energy out in Idaho. And, we're essentially taking stranded wind to drive a couple of electrolyzers here. These are each 40 kilowatt electrolyzers. And the hydrogen that's produced from these electrolyzers isn't used for energy storage. It's literally loaded onto a tube trailer, and it's used for distribution by a local industrial gas company. So in this part of the country, there's not good access to centralized hydrogen production, and so it actually makes economic sense to make the hydrogen with stranded wind and then distribute it from a relatively small production facility like this because delivered hydrogen is so expensive in this part of the country. And then the second just kind of example that I think is really kind of interesting is a project that we did with the University of Minnesota. This is their West Central Outreach Center in Morris, Minnesota. They did a very interesting pilot project that we participated in. It was they had a kind of a ribbon cutting last year for this, and essentially they're taking excess wind power that they have on site on the just off campus in Morris, and they're using that to drive a 40 kilowatt electrolyzer that we supplied, along with a nitrogen generator, which we supplied. And they're feeding the hydrogen and nitrogen to a Haber-Bosch reactor. It's a relatively small reactor. And they're using that to make ammonia. And, one of the interesting things about ammonia is it's really the feedstock for, pretty much all the fertilizer products that are used in that part of the country. And, really a relatively small plant like this, distributed ammonia production plant, can satisfy a fairly significant area of corn production. I think I remember the project director for this from the University of Minnesota saying that 20 tons per day of ammonia production can fertilize about 63,000 acres of corn. So it's a pretty interesting way to capture excess wind energy and basically kind of store it in the form of a commodity chemical that can be used in a distributed fashion.
Hey Steve, just a time check. You've got 5 minutes left.
Okay.
Thanks.
So I'm just going to go fairly quickly through why we think large-scale electrolysis is really a compelling commercial potential. Okay. There's I think we've touched on all three of these new application areas. And especially in in Germany alone, there's a multi-billion-dollar addressable market for these applications. And so we're targeting market entry with a 1 to 2 megawatt electrolyzer starting in 2015. There we go. Okay. Sorry, I got to back up. So just quickly, again, we're sizing this product on our understanding of the market opportunity and where we need to be. We're developing it on a multi-stack architecture. You can see a picture of that stack down below. It's going to be kind of a large active area stack platform, kind of an open frame design approach is what we're looking at. And right now we're doing the trades on where we need to be for the different market applications in terms of capital cost versus efficiency. And this just shows, the next slide just shows a couple of system concepts. Probably the early products we deliver will be in a building kind of format where we set up the stacks and the balance of plant in the building. But ultimately we want to get to a package solution where we install it in 40-foot ISO containers as is shown on the right. And just to show, in terms of the cost, one of the things that we look at is, the cost per kilowatt as a function of, the number of cells per stack. So what this curve just shows is as we reduce the number of stacks in the system, we can significantly reduce the cost per kilowatt of the entire system. So that's kind of part of the trade study, is how big do we make the stack in order to get the cost where it needs to be. And then the next one simply shows as a function of current density, in other words, how hard we drive the stack. If we drive the stack harder, in other words, at a higher current density, we can get the cost per kilowatt down quite a bit as well, because what we're doing is we're getting more hydrogen output out of the stack, for a given capital cost. And here just kind of shows that from a cost perspective, we're already on a second generation, kind of design for our megawatt scale product line, and we've been able to reduce the cost by about 40% just with some design improvements. And just to reinforce the idea that as you scale up, you can significantly reduce the cost per kilowatt. This 7 kilowatt model on the left here, the S series, if you say that's kind of the baseline for cost per kilowatt, as you go up to our larger 175 kilowatt model, you've gone from 100% normalized cost to 28%. So we can realize some very significant cost reduction as we scale up the size. And this bar chart really just kind of sums that up, where as we get up to the 2 megawatt system, now we're at less than 10% of the normalized cost compared to that initial 7 kilowatt model that we started making 10 years ago. And so I think I just have one more chart here, and basically our market feedback is showing us where we need to be in terms of a system cost per kilowatt based on the different value elements that we think we can get out of a large-scale electrolyzer system. And so this just kind of shows for different markets and different applications for the electrolysis where we need to be in terms of the cost per kilowatt. And we think what it does is it really gives us a good basis for setting our price targets for this product, and it assures us that we will be able to hit these targets for these markets. So in summary, what I'd like to say is that really here in the United States, we haven't seen firsthand the kind of issues they've seen with renewable penetration as in Germany. Electrolyzers aren't going to have a play everywhere, but we think for longer duration storage, they will have a significant role. We also think that you need to think of the electric grid and the transportation sector as one kind of cohesive energy ecosystem, and that kind of understanding is emerging overseas. And the U.S. is lagging, I think, most of the world in terms of recognizing and addressing the needs for this kind of storage. So I think that's it.
Great. Thank you so much, Steve. Our next presenter is going to be Tara Schneider-Moran. And Tara, if you give me just a second here, I'll pull up your slides. And Tara, you should have mouse control, so please go ahead.
Great, thanks. Good afternoon, everyone. Thanks for attending today's webinar. My name is Tara Schneider, and I work with the Town of Hempstead Department of Conservation and Waterways. And the main topic I will be discussing today is our wind to hydrogen project at the town's energy park. Sorry. All right, this is a snapshot of the presentation timeline. First, I will give you a little background about the project and its location, and then I'll focus in on the hydrogen station project and then the wind turbine project, because they were both really separate and distinct projects with their own timelines and funding, even though they are physically connected. And finally, I'll discuss how they're operating today and what our plans are for future. First, a little bit about us. The town of Hempstead is located on the south shore of Nassau County in western Long Island, bordering Queens, New York, and we have a population of 760,000 residents, the most populous township in the U.S. And the wind to hydrogen project is sited at the town's energy park in Point Lookout on the same barrier island as the city of Long Beach. And the energy park has been developed by and is sited at the Conservation and Waterways Department. Conservation was always a natural location for the energy park, being an environmental department with an environmental message. We thought it was a great location for clean energy demonstration projects where we could provide information to the local community. And we also thought it was very important to collect data on the energy installations and to share that data with both the education and the energy technology communities. This is an aerial view of the energy park, highlighting the many solar photovoltaic installations. We are demonstrating various types of PV, including single and dual axis trackers and bifacial panels. We also have a house built by NYIT students for the National Solar Decathlon. And this house represents various technologies incorporated into one system. It includes geothermal, solar PV, solar thermal, sophisticated control system, and sustainable materials. We also have two geothermal installations. One is located at the NYIT Solar House, and the other is located at our administration building. On the far western side of our property, we have a Shellfish aquaculture facility where we grow clams and oysters. And the facility is powered by a small wind turbine and solar PV system that both charge a bank of batteries. And the facility requires 24/7 power, which keeps the pumps and motors going, which in turn provide a constant flow of water and food to the shellfish. And so in a power outage event, the facility will run off the batteries, which are continuously charged as wind and solar are available. And this facility actually remained powered up even after Hurricane Sandy, when much of the region was without power for several weeks. And in these photos, you could see the building on an offshore platform, the battery backup, and the wind turbine being installed by town employees. And finally, our topic of discussion for today, located on the east side of the park, is the hydrogen fueling station and 100-kilowatt wind turbine. One of our main goals was to evaluate alternatives to gasoline that can reduce fossil fuel dependency and improve our environment. Another extremely important goal to us was demonstrating hydrogen as a preferable method for the storage of energy. And we also wanted to show on-site generation of hydrogen and blended hydrogen compressed natural gas and the use of these fuels in vehicles. We continue to conduct public outreach and education about alternative fuels and renewable technology. And last, and invaluable benefit to all of these projects was the resulting partnerships and continued relationships with local and national stakeholders to develop hydrogen fueling infrastructure and renewable energy technologies. We had a mixture of both public and private funding to support the wind to hydrogen project. The grant opportunity that really got the whole thing started was NYSERDA's Program Opportunity Notice 1082, which requested proposals that supported the New York State Hydrogen Roadmap and also demonstrated hydrogen internal combustion engine technology. We received cost share from National Grid, our local natural gas utility, through a state alternative fuels tax credit and R&D grant. And we were awarded a grant from the Department of Energy in partnership with our local Clean Cities Coalition to cover the incremental costs of CNG vehicles. The town did as much of the on-site construction in-house to leverage cost share and also reduce project costs. We partnered with Toyota through the Fuel Cell Vehicle Prototype Program. And we received technical support through the U.S. Merchant Marine Academy, who had a solar to hydrogen house at their campus in Kings Point. And also General Motors, their fuel cell division, was very active in the hydrogen industry, also played a huge role in providing technical support to the town. The wind turbine received 100% funding through a stimulus-funded Department of Energy grant, where the town again used our skilled labor force for site construction to reduce project costs. And we received technical support on this project from the National Renewable Energy Lab. And I'm going to focus a little bit now on the hydrogen station for the next few slides. We have many contractors involved with this project, varying roles and responsibilities, and many of these companies have staff with a unique skill set. And we form relationships with these companies and continue to work with many of them today to further the goals of the project. Certain early design elements were included that will allow for future expansion. The original grant application to NYSERDA was for 350 bar fueling. However, it became apparent by the time of the design phase that the hydrogen industry was moving towards 700 bar. And to prepare for this shift, extra conduit and spacing in the layout was included in the design for future 700 bar equipment, should the funding be available. So the station is meant really for demonstration. Only a small number of vehicles can be fueled consecutively. With this in mind, a discharge stanchion was included for connection of a tube trailer, which will provide increased fueling capacity, knowing that we were interested in adding renewables in future. We included the electrical design necessary to accommodate this interconnection. We have 3 fuels at the station. We have hydrogen, compressed natural gas, and a blend of the 2 fuels. First, we wanted to show natural gas, a fuel that is readily available and affordable today, and it's also closely linked to the hydrogen industry. It's a fuel that is similar in properties to hydrogen, and the hydrogen industry has looked to the natural gas industry to develop its own codes and standards. Natural gas is also widely used as a source for extracting hydrogen fuel. And the blend demonstrates a transition to the hydrogen economy and opportunity for hydrogen to enter the market at a more affordable rate while also burning cleaner. And last, we wanted to demonstrate hydrogen fuel that was generated on-site from water, a non-fossil fuel source, was pure enough to be used in fuel cells and was powered by renewable energy. So this is a list of the major equipment at the station. The electrolyzer that we have can produce up to 12 kilograms of hydrogen per day. We have 2 compressors, one for hydrogen and the other for natural gas. We have distinct storage systems for hydrogen and natural gas, blending skid, which blends the hydrogen and natural gas on demand, and dispensers and distinct nozzles for each fuel type. We have vehicles for each of the 3 fuel types. Both the natural gas and HCNG vehicles are internal combustion engines, all converted by a specialized conversion contractor aftermarket. We have Ford F-250 pickup trucks that were converted to run on natural gas, and a shuttle bus that runs on the HCNG. The town partnered with Toyota to utilize several of their fuel cell vehicles through a zero-cost lease agreement, and we really loved having the Toyota fuel cell vehicles here. They were really amazing to drive, and we hope to purchase a fuel cell vehicle when they are expected to become available to the market in 2015. So the hydrogen station was completed in October of 2009, and the goal was to eventually connect the fueling station to renewable energy. In a second phase, when grant funding became available in future, which did happen right as we were commissioning the fueling station. So first I want to talk a little bit about why wind. We were interested in wind energy early on, even before we began looking into developing a hydrogen project. Our department's commissioner was a strong influence in the wind project, as well as our other renewable energy endeavors. And Ron has really provided our small team with the necessary leadership to make all of these projects happen. He had worked with our local electric utility on a feasibility study that was conducted in 2000. And we started meeting with some of the folks involved with that study a few years later, and one of those meetings led to the installation of data acquisition collection equipment to assess our site for wind energy. This was a very important early step to evaluate the technical feasibility of wind. And the anemometers did prove that we had a significant wind resource at our facility in Point Lookout. We continued meetings with other local municipalities, universities, private industry. We were very interested in what others were doing around us and what we could learn from them. This even included some site visits up to Hull, Massachusetts. We visited out on the North Fork to see the turbine out at the Half Hollow Nursery.
Tara, just to give you a time check, you have 5 minutes.
Thank you.
Thank you.
In 2009, just as we were commissioning the hydrogen fueling station, we were notified that the town would receive a $4.5 million grant from the Department of Energy through the American Recovery and Reinvestment Act, known to many as the stimulus funding. The town's strategy for spending the funding was multifaceted. It included around 18 different projects and almost 40 different contractors. The 100 kilowatt wind turbine was just one of these projects. But now this funding gave us the opportunity to finally pursue our long interest in developing wind while also providing a solution to a renewable energy source to power the hydrogen fueling station. The 2 motivating factors for site selection were first, technical feasibility, and second, where could we foster innovation and provide an educational opportunity? We knew we had a wind resource in Point Lookout from both our anemometer data that was mentioned earlier and the small wind turbine unit at our Shellfish aquaculture facility. We performed test bores to determine soil type, groundwater elevation and weight-bearing capacity for the foundation design. Electrical infrastructure was also a consideration. The upgrades that were made to the Point Lookout site during the hydrogen station construction really made it a cost-effective choice with regards to the electrical infrastructure. With the new load from the hydrogen station, our goal was to demonstrate the storage of hydrogen with renewables and the continuing development of the energy park. The Point Lookout really just was the ideal location for the wind turbine. The next phase in site selection was acquiring the necessary environmental permits. The first was an environmental assessment, which we received a FONSI through NEPA. And then following NEPA approval, the project received a negative declaration. The Northern Power 100 was the ideal turbine choice for our site for many reasons. The gearless direct drive feature had less moving parts and lower maintenance costs. The smaller tower height, when compared to megawatt turbines, was really a good choice for the local community. The power size was in line with the existing electrical infrastructure, and this unit was also on the local utilities approved list for net metering, so no power purchase agreement was necessary. And last, because the turbine was funded with stimulus money, we were required to comply with the Buy American provision, and Northern is a Vermont company, so it met those requirements. Some information about the turbine itself. The tower height is at 120 feet. The blades at 35.
And Tara, you have 2 minutes, so they can look at this online after.
Okay. Just some of the performance. This turbine is Northern basically states that it's doing what's one of the best in their fleet. And just to talk about operation and maintenance real quick, the hydrogen station is really not a turnkey operation. It really requires dedicated staff that has an interest in the success of the technology. And in addition, we have night watchmen that work 24/7 and check on the station as part of their regular rounds. The maintenance costs for the station are very high. We found that contracting with key equipment manufacturers for critical maintenance while training our own staff to perform more routine maintenance to be the most cost-effective solution. And also on the wind turbine, which is much simpler maintenance, we are training our own staff to also help with basic operation. So our area was hit very hard by Hurricane Sandy, and because of good planning and design, we had no flooding at either the wind or hydrogen station. It was designed above the 100-year flood elevation, which proved to be enough. There was, however, some minor flooding around the base, so we did perform a precautionary engineering review. And the turbine was fine. We were able to turn it back on. And this also became a real glaring opportunity for a microgrid demonstration. We've done a lot of outreach and education. We've had an extremely positive response from the community. One of the #1 questions we get is, when are we going to build another turbine? We've done a lot of training and workshops, training the local fire department and fire marshal's office, hosted workshops for teachers, providing curriculum training on hydrogen fuel and renewable technology. And some of the next steps for outreach, we'll be building a website, putting some signage out at the facility so people could come and do a passive tour. And then for future projects, we have a range of things that we're working on right now. One of the primary ones is microgrid for the wind to hydrogen project and the integration of stationary fuel cells. We're interested in desalinization and tidal power, and also building out our data acquisition system so that we can share the information publicly. So thanks very much. I'd be happy to speak to anyone directly about our projects. And please don't hesitate to reach out with the phone number there and email provided. Thanks, everyone.
Great. Tara, thank you so much. That was perfectly timed, so I thank you for a very informative presentation to us. Again, I'd like to remind our audience, if you have any questions, to please type them into the question box and hit send. And we're queuing up your questions, and we'll ask your questions following our next presentation, which is by Kevin Harris. Kevin is...
Yeah. Can I say a word about the questions?
Yes.
Kevin, this is Proton Paul. I will be relaying the questions to the presenters after this third presentation for their answers and discussion. We have 87 people participating, and as of now we have one question. And I know that some of you out there have questions. Please enter those now. Don't wait. It really helps in being able to organize the questions and makes it more likely that your question will be addressed.
Great. So again, everyone, type in your question in that question box and hit send, and we'll queue them up and we'll ask them at the end. So Kevin, you're all set to go. You've got mouse control. So this is Kevin Harrison, National Renewable Energy Lab.
Thank you very much. Today I will be talking about a number of things we're doing at NREL. Let me go back one. Basically, the outline of my presentation is to give you a brief introduction. Unfortunately, I do have a repeat slide that Steve showed. I think most people show it when you talk about energy storage, justification of why, explain a little bit about NREL's wind to hydrogen project, and then show you some research results that we've done as we sort of dug into some of these systems and try to better couple them together to improve the system efficiency. So really, why renewable electrolysis for transportation or energy storage or a number of the other feedstocks that Steve has mentioned? There's basically a lot of potential, and there's a lot of different feedstocks, whether it's biomass or natural gas, and of course we're focusing here on renewable energy. I do mostly talk about wind, but I do have some slides on a PV to hydrogen system, which is very analogous, because variable speed wind turbines, much like the Northwind 100 that Tara just talked about, has a DC bus. And there are some synergies there that can be taken advantage of, whether you're producing DC with solar or you have to rectify wild AC from a variable speed wind turbine to a DC bus before you invert it back to AC to go back to the grid. And here's the duplicate slide. You can see at the second range, you can see a lot of the flywheel moving into battery technologies when you have to span minutes of time into the hours. And I drew this green box that should have just appeared for hydrogen and fuel cells, extending up in hours and days, and perhaps even seasonal shifting of wind and solar someday. And that does overlap with the bulk power shown in the upper right of pumped hydro and compressed air energy storage. And some of my slides at the end actually would pull that green box or extend that green box down into the second range, because I show that electrolyzers can respond in the seconds range to help mitigate frequency disturbances and load shifting and things like that, other ancillary support systems that the grid requires. I like to show this graph because wind continues to grow, and the U.S., we have a goal to produce 20% of our energy by the year 2030, and you can see where I put that blue star. In September of last year, we had about 60 gigawatts of installed wind. The darker colors represent states that have installed more, so you can compare your state with some of the leaders like Texas and California. Little deeper into the graph in the lower right, to produce 20% of that wind energy by 2030, we need 300 gigawatts of installed wind. The blue part of that graph represents on land, and even 50 gigawatts at the top, that green swath, represents offshore wind that will be coming soon to the East Coast for sure. So moving on. This is a graphic of what we call here at NREL the wind tech. This system is located at the National Wind Technology Center. It is our wind to hydrogen project. It's surrounded by renewables. You can see PV and wind on the left-hand side. You can see a number of electrolyzers in the middle. Proton's smallest system, that S-series electrolyzer produces about 2 kilograms a day. We did a lot of testing on that system, and is highlighted in the PV R&D we've done that I show in a couple slides. We have their next larger system, the H series, also doing some testing that I highlight later in the presentation. We have an alkaline system from Teledyne Energy Systems. What was interesting about having the Teledyne and the H series PEM is that they're sort of equally paced in terms of their capacity. Both consume about 40 kilowatts. Like Steve also mentioned, they both produce about 12, 13 kilograms a day. So it was nice to put them side by side in a microgrid situation and perform testing on them, and seeing how quickly they can react on a system level. And some very interesting results in that towards the end, so stick with me as we approach the end of this. Down below, we've got multiple compression and storage stages. We do have a 350 bar refueling dispenser up at the National Wind Technology Center, so we are filling fuel cell electric vehicles to about half what they can handle, of course, in terms of pressure. We can also take that energy and put it back onto the grid. We recently decommissioned a 60 kilowatt internal combustion genset from the Hydrogen Engine Center. That's the green box in the right middle. That can export power back, three-phase power back to the grid. And we also have a 5 kilowatt PEM fuel cell with a little inverter inside of it. So we have that whole round trip mini hydrogen economy shown on this graph. And some of the capabilities are on the right. We produce about 1 kilogram a day, and all the other things I really mentioned already, and you can check out later. So this slide just really shows that, in this case, the Alkaline electrolyzer, which has a 33 kilowatt stack inside, can follow a varying signal from a wind. So I call this sort of the classical approach. You read the power that the wind turbine's putting out, take power data from that, and you vary the signal, the control signal you're providing to the power supply that sends current to the stack. And in this case, the blue line represents stack current, and the red is the output hydrogen flow from the system. So, you know, pretty basic way to set up your system and operate it in conjunction with varying wind or varying solar, things like that. So this is where I insert a little bit of PV because I do think it's analogous to variable speed wind turbines, which, you know, have variable rotor speeds that put out what I call wild AC. A lot of people call wild AC, which varies the power in frequency and voltage, and then has to be rectified to DC. And that's where the PV comes in, because PV naturally produces DC. And what I did is I set up a system. I took one of Proton's S-series electrolyzer, which has a 20-cell stack in it, and that's a picture of the 20-cell, and I add an additional 10-cell stack from their smaller unit, and I put them electrically in series. And what I wanted to do is take the 2 wires from the PV array, about a 10 kilowatt PV array, and put it across this new combination of electrolyzer stacks, and I'll show you why that made sense. And I called that the direct coupling, where you literally direct couple the PV arrays to the stacks. And down below, we also designed and built a power converter, a DC to DC power converter that has maximum power point tracking, but also has some inherent switching losses. Whenever you have a power converter, you can see that I put a range of efficiencies for that power converter between 85 and 92%, where the direct coupling really doesn't have any losses, of course, except for line losses, which would be, you know, also applicable to the lower. So essentially 100% connection between the two. And why did I do that? I took that 20-cell stack and I was running it, and I got that red curve in the lower right. That red curve is an IV polarization curve where we swept the current from its highest to its lowest and back, and I superimposed that with the IV curve of the PV array. And the PV array has a natural maximum power point right at the knee, and that's represented by that green diamond. So what I did was, by adding those additional 10 cells electrically in series, I shifted the operating point of the electrolyzer to the magenta, which now rolls up and down that knee of the curve. So it's a better alignment. So I intentionally better aligned the PV array with the electrolyzer stack combination. And what happened? going to the next slide. And this is what happened. The blue curve is the configuration where I had a power converter in between the PV rate and the stacks, and the red curve is the direct coupling, where you essentially you took the wires from the PV array, like I said, right to the electrolyzer stacks. And the direct coupling did better at lower irradiances. So in the morning, in the evening, on cloudy days, you didn't have the losses in the direct coupling, which made it perform better at irradiances less than 500 watts per square meter. And at sea level, at solar noon, the irradiance is typically 1,000 watts per square meter. So that gives you an idea of what an irradiance measurement would mean. So the power converter with maximum power point tracking is the blue curve, and that did better at higher irradiances. So in the middle of the day, on full sun days, so on days of full sun. So the purple curve, if you could take the best of both worlds and direct couple in the morning, evenings, and on cloudy days and switch to a power converter at higher radiances, you could see an overall improved efficiency of 10%. And then that purple curve represents taking the best of both worlds. So moving on to frequency control, I borrowed this this graphic from the website at the bottom, and it basically is a great example of why we need to be able to use electrolyzers, for example, to help the grid. Because when wind and solar ramp, it impacts the frequency. So you can see the line at 60 hertz, and that takes a dip, and then there's 3 phases of recovery. And I'm going to show on the next couple slides that electrolyzers can be used even in this second range, in that blue portion of that graph where things have to be reacting quickly to help recover the frequency during this disturbance. And what I did was I set up a little AC microgrid, and I do realize I've got basically 3 minutes left, and I'll be finishing up quickly. I set up an AC microgrid where I use diesel generators to power the electrolyzers in this configuration shown, and I used the load simulators. It's basically a resistive load to disturb the frequency, as if wind or solar were ramping. And I used the electrolyzers, I commanded the electrolyzers to either add stack power or remove stack power. And in the upper right are graphs of what happens to the frequency sitting at 60 hertz when I slam 10 kilowatts of resistive load on that microgrid. And there's a blue and a red curve. And I didn't use the electrolyzers to do anything. So it took about a second or so for the frequency to recover on this weak microgrid powered by the diesels. And down below, you can look at this later, I commanded the Alkaline and PEMs to go from 100% down to 25% of stack power. And that's that command line, the green, and it took less than, it took about 200 milliseconds for it to reach its new power level. Some interesting results. And this is the results of the testing. You can see that the green curve on the upper right is that natural response where I didn't do anything with the electrolyzers. And the red and the blue represent the Alkaline and PEM mitigation of that same 10 kilowatt resistive load step onto that microgrid. So I triggered the electrolyzers when the frequency deviated 0.2 hertz. So you can see that in the legend. I sort of kept all that information in there for you. And you can see that in duration and magnitude, the electrolyzers help reduce the issues of that frequency disturbance. And I did it in the lower part, in the upper. So I removed 25 kilowatts in this example, and I used the electrolyzers. I triggered them at 60.2 hertz to add stack power. So the alkaline stack went from 15 to 40 kilowatts in the blue curve, and the PEM H series I commanded to go from 50 to 40 kilowatts. And you can see the results, both in magnitude and duration. These things can be used very quickly to mitigate frequency disturbances. And finally, not a big deal, but we want to see, we're running long duration testing on stacks to see if running them in variable mode impacts their life. So we're running thousands of hours on these PEM stacks. Those are the 3 stacks inside of a typical H-series electrolyzer from Proton. We instrumented the heck out of them, and we run variable power to 2 of them. In this case, stack A and B are that dotted green and blue line, and stack C operates at about 120 amps, and they all have the same average power, so we're not running anything hotter, so to speak, than the other. And thank you very much. And since this is being taped, you'll also have access to some references that I left talking about the 20% of wind, PV, and a lot of the testing we've had.
Excellent. Thank you so much, Kevin. We are going to go just a couple minutes over here. We have reached the 2 o'clock hour to handle whatever questions have come in. So I'm going to turn this over to Todd to facilitate any Q&A. Go ahead, Todd.
Great. Okay. Please let me know if you have any trouble hearing me. We do have a lot of questions now, and unfortunately not much time. So I just want to start out by asking if the presenters could address the overall energy efficiency of these systems and the prospects for improvement in that regard.
Yeah, hi, this is Steve, and I'll start off by saying that there's a lot of activity at Proton in terms of improving the efficiency of our electrolyzers. I didn't show any slides on it, but it is something we have presented publicly in the past, that we have a number of research programs focused on improving the efficiency, especially at the cell stack level, since that is a significant area of opportunity. But even in the balance of plant, there are opportunities to improve efficiency in the drying system as well as the power conversion system. So there is quite a bit of activity to reduce the energy consumption required to make hydrogen via this process.
Okay. Question for Tara. What's the levelized cost per kg, or I guess however whatever unit of measurement you use, for hydrogen over this project's lifespan?
Well, we're not selling the hydrogen publicly, so we don't have a rate at what the cost is. And as far as trying to understand our operating costs and basically the whole efficiency of the system, we've just added metering systems. So we're going to be taking a closer look at the load profile, and hopefully that's something we're going to be studying going forward.
Okay. A couple of questions that are comparing this to germ systems. One, and I'm going to kind of put these together. One person wanted to know whether the hydrogen storage could be done on a seasonal basis rather than just on an hour or day basis, as I guess is being tried in Germany. And another person wanted you to talk a little bit about bringing down costs. And the specific question is that the German power-to-gas wind hydrogen costs are approximately 10 times wholesale cost of natural gas on an energy equivalent basis, according to the questioner, which is too high to use this on a large scale. So what's the best way of reducing the costs?
Yeah, hi, this is Steve again. I think Kevin did mention in his chart on the segmentation of hydrogen energy storage that there is the potential to do seasonal kind of energy storage, and and I would agree with that. I think that you certainly there is the opportunity to do that kind of time scale with this approach. And then, I mean, again, as far as the cost thing is concerned, we are aware that some of the cost targets for power to gas and some of these other applications are pretty aggressive. I mean, we're looking at some cost targets that are down under $1,000 a kilowatt for the electrolyzer unit, and those are aggressive, but we think we have a pathway to hitting those kinds of cost targets through the the scale up and cost reduction activities that we have ongoing.
Okay.
Just to add to that, we're at the Town of Hempstead, I'm not sure that seasonal storage would make sense, but we are operating our Proton Electrolyzer at night when we have an off-peak rate. So especially in the beginning, the first 2 years before we had the wind turbine, this helped us lower our operating costs. We have some of the highest electric costs in the country here on Long Island. So we were operating the electrolyzer at night, and also something we're looking into is virtual net metering, so we can use some of the wind generation in other locations where we also have load.
Okay, great. Question for Kevin. Do you need batteries in and the electrolyzer? And is the AC-DC converter the only power conditioning component between the turbine and the electrolyzer? And finally, what is the percentage of total cost that would be allocated to power conditioning components?
Okay, a few questions there. The first one, do you need a battery? I think I understand the question correctly. Do you need a battery in the electrolyzer? You don't necessarily need a battery. We were running those systems basically real time. In the case of the PV testing, we took whatever energy the sun gave us in that direct coupling versus power converter. So we didn't have any batteries in that system. Remind me of the next part of that question. Sorry.
I think that the next part was what percentage of the overall system cost is attributable to the
power converter.
Yeah.
Yeah. Okay.
Power conditioning equipment.
Yeah, I think in general Steve would be better at that, but just sort of the rule of, well, some guidelines, and these are just general numbers. For an electrolyzer system that Proton might sell you, the stack represents perhaps about 50% of the cost of the system, and the power conversion. Just using general numbers, Steve can put a little more fine-tuning on this, but the power converter might be 25% of the overall system cost.
Yeah, that's not far off. I think stack cost might be a little closer to 40%, but power conversion, yeah, probably around 20%, something like that.
Okay. Here's another question for Steve. If your power input price were zero, so I mean, I guess that would be, if you're sourcing all your power from on-site renewables, for example, what type of price would you need to receive on hydrogen to make electrolysis economic?
Well, I'm not sure there's an easy question to that, but I will say in general, about 2/3 of the operating cost of the electrolyzer is the cost of the electricity, and that's based on some nominal kind of rate of 5 cents per kilowatt hour, which is pretty cheap. So when you can eliminate the cost of the electricity to run the electrolyzer, boy, you make the economics a whole lot more attractive. And so that's where the idea of using stranded wind power, for example, really does make economic sense rather than using grid power to make the hydrogen and then hoping to recover the cost of that grid electricity. So it's very significant. Eliminating the cost of the electricity is a very significant economic factor.
Somebody actually, you mentioned stranded wind. Somebody actually asked, what is stranded wind? I'm assuming that refers to wind that energy that's produced but can't be sold onto the grid or used otherwise on site. Is that what we mean when we say that?
I don't know, Kevin, is there a technical definition for it?
For stranded wind? To me, it means a couple different things. It could be curtailed wind, where in certain regions and in other countries where the grid, in the middle of the night, for example, you can't turn down your base load power plants any further, like coal and nuclear, and they may have to turn off the wind. That's sort of stranded wind that would come at a near free price. But there's also wind in the middle of North Dakota and South Dakota that doesn't have access to transmission lines that I see as sort of a stranded, renewable stranded wind opportunity where, you know, like the example you gave, Steve, for Idaho, where those wind turbines were powering the electrolyzers directly. That's sort of a stranded wind in another case.
Okay. What is the loss factor over time for hydrogen? In other words, at what rate does it escape if you're storing it over time?
I mean, I guess I'll say that you know, it literally could be zero. You know, it's, you know, we store hydrogen at our fueling station here at Proton, you know, for long periods of time in pressure vessels that are very impervious to, you know, to hydrogen leakage. So, I mean, there isn't kind of a you know, a standard leak rate that you have to deal with. And that's actually one of the beauties of hydrogen, is that you really can store it for long periods of time, and you don't lose any of the energy value from it sitting around, you know, unlike a battery where, you know, you're constantly losing, you know, the energy storage in the battery. So hydrogen is great from that standpoint. You can store it long periods of time, and it doesn't lose any of the energy value.
And I agree with that. You do, when you're dealing with higher pressures or dealing with valves and other components that do leak and change with temperature. So here in Colorado, we have a fair amount of temperature swings, and we go out and we leak check our tanks and our valves, and we find leaks. But like Steve said, these are seamless steel vessels. They're ASME pressure vessels that should be able to contain the hydrogen for long periods of time. Regular maintenance looking for leaks is not uncommon for hydrogen because it is such a small molecule. I think you do get into other issues if we move towards seasonal storage or long duration, where you think about storing instead of air in underground caverns. What if we stored hydrogen in these large underground caverns? And I think there would be a leak rate where hydrogen would diffuse out of those at some rate, but I don't have that number.
I'm aware that we are over time. I'm going to, I think, wrap it up with one last question here. I'm sorry that we did not get to all the questions, but this one is something that you may all be able to speak to. And the question is, could any of the presenters discuss a case study of a remote microgrid using this technology? So any kind of islands or remote community, remote mining, islanded small grids. Does anybody know?
I don't have any good examples of. I know there is a large effort in Hawaii, which would be seen as a large microgrid, where they're using electrolyzers for some grid stabilization efforts, sort of like the microgrid experiment I showed you at the end of my presentation. So I think Hawaii could be seen as a microgrid case example where they have large penetrations of PV, and they want to make hydrogen and use electrolyzers in unique ways to mitigate grid and provide ancillary services to the grid.
Yeah,
are they actually doing that now? Do you know, or is that something that's sort of in the planning?
Steve probably has a good handle on what systems they have out there.
Yeah, yeah, the microgrid program that's kind of gotten a lot of attention it's actually a DoD-sponsored program called Spiders, and it's a three-phase program. They did an initial circuit-level demonstration at Joint Base Pearl Harbor Hickam in Hawaii. The second phase of that program is being done at Fort Carson in Colorado, And then the third phase is they're going to do a whole base microgrid at Camp Smith in Hawaii. And there is some element of energy storage in that one, although unfortunately the hydrogen piece of it got scrubbed in the first phase. So, but I think that is a good example of a project that could benefit from hydrogen energy storage.
Okay. Tara, were you going to say something there?
No, I mean, just to add what we had already talked about on the presentation, that we're very interested. That's definitely our next phase at this site, is to integrate microgrid technology.
Okay. There were a few people that were interested in asking more questions about your system in Hempstead. Can they contact you, or is there a way for them to get information on a website or something?
Sure, yeah, I'd be happy to talk to them directly. They can use my email or the phone number. I have my phone number listed on the slides. Be happy to talk to anyone about their questions.
Okay, great. And your email should be showing on everybody's screen right now. And I just want to make one more comment that one of the participants has written that the island of Utsira off the coast of Norway represents an example of a microgrid using this technology. So I don't know about that one, but it sounds interesting. I'll have to look that up. So I think we're going to have to end this. Thank you very much for an excellent webinar. And again, I'm sorry to the participants whose questions we were not able to answer. And Maria, any final comments?
No, just that again, this has been recorded, and you should be able to find the recording on our website along with PDFs of the presentations probably by the end of the day today. So look for that at www.cleanenergystates.org/webinars. And also you'll be able to find on our website a page to sign up for our newsletters and e-distribution lists to be made aware of other events pertaining to fuel cells, hydrogen, or energy storage and microgrids. So with that, I'm going to conclude this webinar and thank again our guest speakers for joining us today for their very excellent presentations. So thank you to Steve Szymanski, Tara Schneider, and Kevin Harrison for being with us today. Thank you, the audience, for tuning in, and we'll be in touch again for an upcoming webinar from the Clean Energy States Alliance. Everyone have a great day.